Concrete sleepers form the backbone of modern railway systems, and their production follows a highly structured process. The factory adopts a carousel system, where a limited number of molds circulate in a continuous loop. The process starts with material acceptance and preparation of armor wires. These wires are distributed into molds, screwed, and fixed with plastic dowels. Grain size distribution of aggregates is monitored to ensure reliable concrete composition. Every check reinforces the sense of trust in the materials being used. Next comes casting and vibration of the concrete. The molds are transferred into a steam room, where concrete strength is measured at both 12 hours and 28 days. The anticipation of these results highlights the importance of timing in production. After curing, molds are unscrewed and emptied, while stressing operations secure structural integrity. Final stages include fastening, sealing, and finishing, followed by packing and storage. Quality checks, static tests, and precise measurements certify each sleeper. Reaching a productivity of up to 1,200 sleepers per day feels like seeing efficiency at its peak.
Heat shimmers across the desert near Abu Dhabi, where the Etihad Rail project is reshaping the landscape with steel and determination. The Shah Ruwais railway line extends for 416 kilometers, linking vital industrial zones across the UAE. This project is more than a connection. It's the backbone of a growing logistics network across the Emirates. The work opens at the welding plant, where long rail sections are prepared. Prime rails are loaded, aligned, and flash butt welded to create continuous lines. Each weld must endure desert heat that can reach 50 degrees Celsius, demanding unmatched reliability. Every joint undergoes testing before being cleared for track assembly. N. Next, a layer of ballast is spread across the graded terrain, forming the bed for rails and sleepers. The MCB-01 track laying train, patented by SALCEF, positions each segment with GPS guidance. The sheer coordination between machines looks like a moving factory across the desert plain. Fastenings are secured, rails welded again, and surfaces ground to perfection. Then ballast filling and tamping stabilize the structure, followed by topographic surveys ensuring exact alignment. A second ballast layer and further profiling refine the line. Track leveling, alignment, and dynamic stabilization simulate the passage of 50,000 tons of load, testing its readiness before real freight ever runs. You'd never guess how much precision hides behind each meter of rail work. Final stages include cleaning sand with vacuum systems, de-stressing, aluminothermic welding, and safety inspections. Zero-accident philosophy guides every phase, a mantra echoed across the site. The result? The UAE's first national railway, connecting Shah, Habshan, and Ruwais. Proof that even the harshest desert can host a thriving artery of movement. That line, slicing through sand, almost feels alive, pulsing with future trade and energy.
The T1 track gang moves swiftly along the CE&D sub, replacing railroad ties between Princeton and Vincennes, Indiana. Every action is coordinated, from lifting old ties to positioning new ones with precise alignment, ensuring trains can run safely. Workers remove worn wooden ties using hydraulic tools, prying them free while checking for ballast stability. 10. It's impressive how quickly each tie is lifted and swapped without slowing the train schedule. Once removed, new ties are set in place, and spikes and plates are secured to anchor them firmly to the rails. Mechanical jacks adjust track height and maintain alignment across uneven ground, preventing future wear. As the team advances, ballast is leveled and tamped around the new ties, stabilizing the track and improving drainage. Some movements almost seem rhythmic, though the real skill lies in anticipating how the track will settle under train loads. Each segment is checked visually and with measuring tools to ensure uniform spacing and consistent gauge. In hydraulic and manual systems work together as spikes are driven, plates positioned, and rail ends aligned. You can really appreciate the combination of muscle and technique in a task that looks deceptively simple. Occasionally, the crew halts to double-check alignment or swap tools, showing a keen awareness of safety and precision. Machines handle the heavy lifting, yet human judgment guides every critical step. The track slowly regains its strength, each tie a small testament to the coordination required on a railroad project. Dust rises as tampers compress ballast, and the sound of spikes being driven echoes like a heartbeat along the rails. Even small adjustments are crucial, preventing misalignment that could compromise train safety. After the new ties are anchored, the ballast tamper moves along the track, compacting and leveling the gravel around each tie. This ensures the track remains stable and properly aligned under heavy train loads. The tamper vibrates and presses simultaneously, filling gaps and preventing uneven settling. Operators monitor the process closely to maintain consistent height and gauge. Small adjustments are made in real time to prevent misalignment as the machine advances. By the end of the shift, the CE&D sub stretches smoothly with new ties in place, ready for normal train operations. The teamwork between the T1 gang and their equipment makes the replacement process efficient, controlled, and surprisingly satisfying to watch. One moment a tie is removed, the next a fresh one is firmly anchored, keeping the railroad running seamlessly. Those spikes might look ordinary, but each one represents hours of planning and coordination condensed into seconds. Concrete pours into the Gomaco GP4, and operators guide it forward across the airport runway with steady coordination. Concrete flows into the paver, and the massive machine glides steadily across the runway, shaping each lane with exacting consistency. The combination of speed and precision is surprisingly smooth for such a colossal piece of equipment. Operators synchronize the TC5600 texture/cure machine immediately behind the paver, imprinting the concrete surface while ensuring proper curing. Sensors monitor the surface continuously, adjusting pressure and texture as needed. That straight stretch of runway looks like it's being leveled by a giant sculptor rather than a machine. Once the concrete sets, the team inspects each lane for uniformity. Any deviations are corrected by fine adjustments on the paver controls. The coordination between human operators and heavy machinery is remarkable to watch unfold naturally. The GP Force tracked mobility allows it to maintain constant contact with uneven subsurfaces, reducing gaps and imperfections. Meanwhile, the TC5600 ensures grooves are crisp and the surface is ready for aircraft use, and didn't expect a runway to get such a sleek finish in just hours. That groove pattern almost makes you want to run across it barefoot. Compact Lee-Boy machines are ideal for small-scale paving and confined urban areas. Operators align the paver carefully to maintain smooth edges, avoiding gaps that could compromise road integrity. Hydraulic systems adjust automatically to changes in surface elevation, ensuring an even layer across the entire path. Material flow is regulated to prevent clumping or voids. The small size of the machine allows it to maneuver tight spaces that larger pavers cannot reach. Each pass combines human oversight and machine consistency for roads that last longer and perform better. That quick adjustment on the fly almost looks like the machine reads the surface ahead. Cranes and crews maneuver enormous girders over osportos, each movement deliberate and controlled. Cranes lift massive beams into place, while workers guide them with exacting care to align perfectly with the lattice system of 24 meters. The project progresses through sequential phases, each one building on the last to form a continuous elevated track. Formwork and scaffolding provide support as concrete is poured and cured, ensuring stability and safety. Engineers monitor stress points to prevent deformation and maintain the viaduct's precise geometry. Mechanical systems and human skill synchronize as cables are tensioned and connections secured. The pace of work is steady, yet every movement matters, balancing speed with structural integrity. You wouldn't expect such intricate teamwork to be so fluid at this scale. As sections complete, the elevated line begins to take shape, bridging valleys and rivers with engineered grace. Strong steel bars are shaped into perfect spirals using the RMS spiral machine. Two independent motors control every roll, forming hoops and coils with exact diameters. The microcontrol panel lets operators program turns, sizes, and even store settings for later runs. Heavy-duty construction keeps it stable, while the horizontal module pivots away for longer spirals. Pure engineering efficiency at work. Nimtet laid.
Coastal defenses rise where land and sea struggle for balance. TechFab geotextile tubes are filled with locally sourced sand, creating resilient barriers against waves and currents. The process starts with tube placement, forming the core of breakwaters, revetments, and seawalls. Next, filling operations stabilize the structure, while filtering layers allow water flow but retain infill. Additional scour aprons secure the base from erosion. With tubes sized and arranged to project design, coastlines gain strength and protection. The scale feels both industrial and natural.
Speed, precision, and innovation converge in the TUPO-8, a machine redefining wall plastering on an industrial scale. This isn't just a tool, it's a breakthrough built for performance and endurance. Its power instantly draws attention as the frame moves with an almost mechanical confidence. NTHE operation opens with the folding of lateral poles, allowing the TUPO-8 to glide smoothly across construction sites. Once in position, its digital auto-positioning system locks the alignment with flawless accuracy, ensuring every stroke of plaster is even and consistent. The engineering behind this alignment system shows how digital control is transforming manual labor into pure efficiency. Next comes the extra-large mortar tray, a design meant for non-stop work. It's wide enough to be refilled directly from a wheelbarrow, eliminating downtime and keeping productivity constant. That seamless refill motion says everything about how well thought out this machine truly is. When activated, the TUPO-8 covers up to 200 square meters of wall per hour, a feat that speaks volumes about its power and reliability. Anyone seeing this in action can understand why professionals call it the ultimate plastering partner. Then STC, one STC, you inactivate, then STC 2 inactivate, then STC 2 inactivate, you inactivate 2 inactivate, any 2 inactivate, then STC. Power equipment brings energy straight to the concrete pour. The hydroscreed is mounted on rails, guiding its rolling action across the fresh surface. It's satisfying to see the long pass flatten every section. Crews follow with bull floats, smoothing edges and filling minor gaps. The uniform floor left behind looks rewarding. On a wide construction site in Beaufort, Georgia, trucks from Ernst Concrete arrive, with load after load of ready mix. The project is a large warehouse slab-on-grade for Martin Concrete Construction. The scale of the pour instantly sets an impressive atmosphere. Drivers position the chutes, releasing steady flows of concrete into prepared sections. Workers guide rakes and shovels to spread the mix evenly across the subgrade. Laser-guided equipment ensures thickness stays consistent with the engineering design. Watching the gray surface expand feels like seeing progress come alive. Crews coordinate movements so no area sets too quickly. As placement continues, bull floats glide over the surface, smoothing ripples and leveling excess material. Edges are straightened and control joints are marked for durability. The teamwork at this stage adds rhythm to the operation. Power trowels then follow, refining the surface to achieve a flat and durable finish. By the end, the warehouse floor extends in a continuous stretch of solid concrete. It is remarkable how the site changes within a single day. The uniform slab speaks of both planning and effort. Every step shows why concrete remains the foundation of modern building.
Pipes this wide don't just fit together. They have to be fused like one continuous piece of plastic. That's exactly what Gem Industrial's McElroy Trackstar machines pull off day after day. Their use of McElroy Trackstar fusion machines brings power, control, and unmatched accuracy to pipe joining. Each weld isn't just heat and pressure, it's the difference between a pipeline that lasts decades and one that fails too soon. That's the kind of reliability major civil and industrial projects depend on. The process begins with pipe preparation. Ends are trimmed and cleaned to ensure full contact during fusion. Any misalignment could affect pressure integrity later, so every millimeter counts. The Trackstar unit clamps the pipes securely, and heating plates are positioned to soften the HDPE material to the right temperature, N. Once molten edges meet, the fusion is permanent, almost poetic for plastic. A quick thought pops up. If only some arguments could be solved this cleanly. After the fusion, each joint is cooled under constant force, maintaining alignment and pressure. GEEEEEM technicians use electronic data logger systems to record every weld parameter, temperature, pressure, and time, ensuring complete QA traceability. No shortcut survives here. Data becomes proof. The information is then reviewed for compliance before the pipeline is cleared for hydrostatic testing. The company's dedication to quality control explains why their welded systems handle thousands of liters under pressure without fail. Next, pipes are positioned using roller supports and transporters, preventing strain before backfilling. Concrete saws and cutters prepare surrounding structures, finalizing the installation. The job might look repetitive, but consistency is what defines great welders. One slip, and the whole section goes back to redo. No room for ego on this site. McElroy Trackstar 500-900 units stand out for their self-propelled design, capable of welding diameters from 180mm to 900mm. Wireless remote control gives operators flexibility in tight sites, and their electronic data systems tie perfectly into GEM's QA framework. The hum of hydraulics and the quiet confidence of the crew make a strong combo. No drama, just flawless work. Every fusion finished here represents the unseen strength of infrastructure built to endure.
"10 days of dedicated work bring the Braille townhouse from foundation to finished two-story walls. Every movement counts, balancing speed with absolute accuracy. The bricks arrive on site pre-sorted, so masons can maintain a smooth workflow without delays. The first layer of the wall is set on a protective bitumen membrane, keeping moisture from rising into the bricks. A specially mixed cement mortar acts as the foundation, compensating for any unevenness in the floor slab. Corners are carefully established first, as they guide the rest of the wall. Even the small adjustments to the corner bricks are critical for the stability of the whole structure. Didn't expect them to align the first row so perfectly with lasers. It's like magic for the eyes. Masons follow exact measurements from the blueprint for window and door openings. On the south side, 3 floor-to-ceiling windows require pausing the brick row. The walls gradually rise as stones are laid row by row, connected using thin bed mortar for strong adhesion. Each layer of mortar is applied evenly to maximize energy efficiency and wall strength. Poroton bricks provide excellent thermal insulation and soundproofing, all without an external insulation system. This explains why the family chose BRALE. They wanted that homogeneous masonry advantage. Next, the masons install the moisture barrier again and finish the 2 bottom rows, forming the base, ready for later cladding. For the upper walls, each brick is aligned using laser, spirit level, and guideline cords. Interior walls use thinner 11.5 cm plan hooglocht ziegel, while load-bearing walls use 17.5 cm bricks. Every opening, every wall follows the detailed blueprint, ensuring exact placement. Scaffolding is set and supports positioned for the ceiling. The semi-finished concrete panels, reinforced in advance, are laid in place. Additional reinforcement bars tie the panels to the masonry and connect the segments together. Styrofoam covers protect conduits for water, heating, and electricity. Vibrators compact the concrete, eliminating air pockets and giving the ceiling a dense, even structure. That pull of the concrete vibrator looks deceptively gentle, but it shapes an entire floor's strength. Upper floor walls follow the same technique, corners first, then exterior walls. Non-load-bearing partitions are built with a narrower Poroton bricks. Finally, the ring beam is formed atop the walls with reinforcement steel and poured concrete, compacted to lock the masonry in place. After 10 days, the two-story Braille townhouse stands complete. Feels like watching controlled force and craftsmanship frozen in perfect form. And somehow, all these steps happen faster than you'd expect, almost like the house grows itself. The combination of precise planning and skilled hands makes the entire construction flow seamlessly. Even small finishing adjustments are made immediately to keep the workflow consistent. In. 60,000 tons of melamine leave Qatar Melamine Company each year, contributing 5% of global output. Operators monitor the process from a high-tech control room, ensuring precise packing into 25-kilogram paper bags or 500 to 1,000 kilograms polypropylene sacks. Melamine's versatility powers resins, insulation, and pigments worldwide. Those big bags stack like miniature towers, seriously impressive. Untully. Aerial views over the Ankara-Nigda highway reveal the scale and complexity of modern road construction in Turkey. From the main control center at AKM Kapgagi to key junctions like Ahibos, Emirler, Kulu, and Bozkir, traffic flow and infrastructure are carefully coordinated. Construction crews can be seen adjusting barriers and signage to ensure smooth progress along the route. Survey teams are regularly measuring lane alignment to maintain precision. The highway stretches over several kilometers, connecting major viaducts such as Derekigli Viadugu and Bozkir Viadugu alongside bridges like Kizilirmak Geçiş Köprüsü. Each structure is monitored for alignment and safety, ensuring long-term durability under heavy traffic loads. The helicopter inspection highlights how planners and engineers coordinate multiple construction zones simultaneously. Seeing the scale from above gives a different appreciation for the work. Concrete pouring continues on select bridge supports while asphalt layers are applied on new lanes. Temporary traffic cones are installed to guide vehicles during construction. At various points, KM 11 plus 780, KM 29 plus 600, KM 51 plus 900, KM 73 plus 800, and KM 180 plus 089, traffic interchanges and toll booths are integrated into the design. These systems allow for efficient vehicle movement and management of toll collection, minimizing congestion along the route N. The route also passes through more rural junctions like Agakorn Kavsagi, Derinkuyu Kavsagi, and Golchuk Kavsagi, showcasing how modern highways blend urban planning with regional accessibility. Bridge sections, such as Kizilirmak Geçiş Köprüsü, demonstrate structural engineering precision, allowing the highway to span natural obstacles without disrupting the environment. N. Temporary scaffolding is positioned under certain viaducts for inspection purposes. Drainage channels have been installed to prevent water accumulation during heavy rains. Construction workers are testing guardrails for stability along sharp curves. During the inspection, Minister Adil Karasmailoglu assessed progress, focusing on traffic flow, junction efficiency, and viaduct integrity. Helicopter surveillance provides real-time feedback, allowing adjustments before the final completion. It's almost like seeing a board game, where every piece needs to be in perfect place before moving forward. In an A. Workers operate cranes to lift precast concrete sections into position. Signage poles are being anchored firmly along the highway shoulders for future traffic guidance. Survey drones capture imagery of ongoing work to track project timelines. The Ankara-Nigdi Highway exemplifies integrated infrastructure management. Tunnels, bridges, viaducts, toll plazas, and interchanges are interconnected to ensure smooth operation and safety. The project balances technical excellence with practical design, making it a reference for large-scale highway projects in the region. From the main control center to the final viaducts, every segment is designed with efficiency and safety in mind, emphasizing that modern highway construction is a complex orchestration of technology, logistics, and human coordination. The Komatsu bulldozer pushes scrapers along the irrigation canal, moving soil with controlled intensity. The powerful machine grips the uneven soil, gradually deepening and widening the channel with each controlled pass. The way the soil shifts under such force is almost hypnotic, like watching raw energy in motion. Each scraper has been precisely calibrated to match the specific soil type, allowing maximum efficiency. N. Operators guide the scrapers carefully behind the bulldozer, ensuring that the soil is collected and transported efficiently. The first action involves aligning the scrapers precisely to match the canal's contour. Hydraulic arms adjust automatically to maintain optimal angle and depth. Even subtle changes in terrain are absorbed seamlessly by the machine's adaptive hydraulics. You wouldn't expect such smooth coordination from machines of this size. N. As the bulldozer advances, soil is pushed forward into the scrapers. Each load is evenly distributed, preventing uneven banks and ensuring a uniform canal depth. Sensors and operator adjustments constantly monitor soil density and moisture levels. The bulldozer maintains traction on uneven patches, keeping a steady pace across the canal, while the scraper wheels compact the soil slightly as they turn, stabilizing the canal floor. That pull from the bulldozer feels stronger than it looks on screen. Once the scrapers reach capacity, the machines swing the loads to the side, depositing soil where it reinforces embankments or fills low areas. Operators maintain a constant rhythm, balancing speed with precision to keep the excavation consistent across the canal's length. Engine temperature and pressure are monitored continuously to avoid interruption, and operators make small, real-time adjustments to improve bank stability immediately. Visual markers along the canal help operators maintain perfect alignment during each pass. Alignment checks are performed multiple times per pass to ensure uniformity, while hydraulic pressure spikes are absorbed by integrated safety systems. The teamwork between human skill and Komatsu engineering is impressive without being flashy. Toward the final stretch, the bulldozer makes finishing passes, smoothing banks and correcting minor deviations. The irrigation canal emerges with uniform depth and width, ready to support water flow efficiently. Hydraulic and mechanical systems work seamlessly to reduce soil loss and prevent collapse. Scrapers leave minimal gaps between loads to reduce cleanup efforts, and angle adjustments prevent overcutting of the canal banks. Maintenance checks occur throughout the shift without stopping work, and soil compaction patterns are visually verified for uniform results. NTHAT soil pile almost looks like a natural sculpture after each pass. Seeing the bulldozer push like that makes you wonder how much power it packs under the hood. High mountains set the stage for the Diamer-Bhasha Dam, where construction advances with immense energy. The scale is staggering, and each segment shows how engineering reshapes the landscape. The atmosphere is filled with determination as the site pushes forward day and night. Work begins with the diversion tunnels, 2 inlets and dual outlets prepared to guide the river. The diversion canal and downstream cofferdam stabilize the flow, allowing progress on permanent foundations. Each stage looks like a massive challenge, yet it moves with remarkable order. On the right bank, power intakes rise, while a permanent bridge downstream strengthens access. The aggregate plant and HFO plant supply vital materials and fuel, ensuring operations never slow. The coordination across areas reveals the discipline behind such a colossal task. Batching plants on both sides provide concrete non-stop, supporting abutments and relocated roadworks. Every structure adds weight to the vision of 500 megawatts power. The completion of Baihetan hydropower station's main structure marks a turning point in large-scale energy construction. Built along the Jinsha River, it holds an installed capacity of 16 million kilowatts, generating over 62 billion kilowatt-hours annually. Engineers highlight 2 innovations: upgraded units reaching 1 million kilowatts, and turbine runners combining long and short blades for stable operation. Compared with the Hoover Dam, its scale is astonishing, delivering renewable energy and reducing emissions by 51 million tons yearly.